Good morning, good afternoon, good evening, whenever you may be. It's another day of exciting science action live from the Brenna Bunker in the quarantined Southeast United States. It's 7.E.1 Earth Systems. We're doing atmospheric pressure for the second day in a row. I hope everybody's had a great day yesterday. I know mine was pretty good. It was my wife's birthday yesterday. She turned 25 for the 19th time. But we had a great day, did some neat things, just a little bit out of the ordinary, but best we could do under the conditions here of quarantine. I hope everybody else has had something to do in the last couple of days. I know enough of you are checking in with some of the math, some of the science. Just remember, when you watch these videos, check in the comment section. That is your attendance for the day. And make sure you like the video and subscribe to the channel. All right. So, once again, we're doing Earth systems. We're talking about air pressure. Again, yesterday we talked about air pressure and what air pressure actually was and where it originated from. Remember, air pressure literally is gravity affecting the mass of the atoms of the column of air that's above the point where the pressure is being taken. So today we're going to talk about some more reasons why air pressure may vary. So yesterday we just basically said if you went up in altitude, so if you went from the sea level up into, say, Denver at a mile-high altitude, your pressure is going to change. Remember we said about, there's 80 kilometers of atmospheric gas above us, but yet half, you go up 5.5 kilometers and half of the pressure is gone. So remember, most of those gas molecules are concentrated in the lower portion of the atmosphere. So today we're going to talk about other ways that air pressure can vary besides altitude. So go down here, it says the amount of water vapor in the air. Water vapor, remember, water vapor is water that's been turned into a gas, right? In the air has an effect on air pressure. The more water vapor in the air atmosphere, the lower the air pressure. Now you got to think, it's like, wait a minute, we're loading more things in, and yet the pressure goes down. And because usually more things means more mass would mean more things for gravity to have an effect on, and it doesn't work that way. So now just listen to this whole thing before you kind of go, man, it doesn't sound right, and just listen. All right, so when you look at it scientifically, and we invite our friend Avogadro to help us out, it makes more sense. If we have a box of air that is a cubic meter, so basically it's a meter by a meter by a meter, right? So we're talking about a box of air. And our buddy Avogadro says if we take the air, we take the molecules inside of there, we're going to know exactly at a certain temperature and a certain pressure how many actual molecules are going to be in that box, like the number of molecules. So, and you'll hear this later in chemistry and science going forward. It's called Avogadro's number. It's a constant. So if we have air in a box, we can calculate the number of atoms and molecules that are in the actual space. Our atmosphere is 78% nitrogen and 21% oxygen with 1% other. That right now we're going to kind of ignore that 1% of other stuff, because when we're talking about the number of atoms, there are too few to really be meaningful in these examples. So nitrogen in the free state is not a single atom of nitrogen. It's actually two atoms of nitrogen put together. These two atoms put together are bonded together, and so they become a molecule. That's why I keep saying the word molecule, because it's not just individual atoms of pretty much anything that's floating around the atmosphere. So these things are molecules, and nitrogen is two atoms bonded together in a molecule, and they weigh 28 AMU, which is atomic mass units. And that's the total of 214 AMU nitrogen atoms. So oxygen is a two-atom molecule as well, weighing 32 AMU. That's 216 AMU oxygen atoms. Now our buddy Avogadro says that at a given pressure, all right, this is the pressure we're talking about, and a given temperature, the temperature is going to be, 18 degrees Celsius, and the pressure is going to be 1,000 millibars. A box will contain, we're just going to use round numbers. So a 15C and take 1,000 millibars approximately takes 1,000 molecules of gas. Just to make the numbers easy. Actually, is it 1,000 molecules? No, it's way higher than that, but we're making numbers easy to play with. So normal atmosphere mix will make that 780 nitrogen molecules with 210 oxygen molecules. Now remember, water is H2O. That's 2 hydrogens and 1 oxygen. The important part to recognize here is that water weighs 18 AMU. 116 AMU oxygen atom and 1 AMU hydrogen atoms. Remember, 18 AMU. The nitrogen and the oxygen that were already there weighed 28 and 32. So go back to our block of nitrogen and oxygen. Avogadro tells us the number of molecules must remain the same given a certain temperature and a certain pressure. So if we put in some water vapor molecules, some nitrogen and oxygen molecules have to leave. Remember, the water vapor molecules weigh 18, whereas the molecules that are getting kicked out weigh 28 and 32 respectively. So for every water molecule we put into the box, the less it weighs. The less it weighs, the less pressure it can apply. So the higher the level of water vapor into the air, the lower the air pressure will be. Remember, because the box contains 1,000 molecules only. It can't contain 1,001, it can't contain 1,002. So every time water vapor goes into the box, one of those nitrogen molecules or one of those oxygen molecules gets kicked out. So every time you add water vapor to the atmosphere, the air pressure goes down because the mass is less. Every time you add water vapor to the atmosphere, the mass goes down and the air pressure is less. Interesting. Doesn't make, because it's like, hey, wait a minute, we're adding 2. No, we're displacing things that weigh more. Think of it that way. Not adding 2, we're displacing. We put this in, something else goes out. Something that we're putting in that weighs less. It's like having a box full of barbells and taking a barbell, a weight out and putting a stuffed animal in. That's what you're doing every time you add a water vapor molecule to the atmosphere. You're taking a weight out of the box and you're putting a stuffed animal into the box. That box now weighs less. You do it enough times and that box weighs significantly less. So water vapor can make up anywhere up to about 3% of the atmosphere. So if you put enough water vapor in the air, you definitely can change the air pressures, a fairly significant amount. All right, so the last thing we're going to look at here is how air pressure varies with temperature. So now again, temperature rises. As temperature rises, the individual molecules will move faster. Because remember, temperature itself is a measurement of the average kinetic energy of the item. Whether it's a solid, a liquid, or a gas, temperature is simply a measure of the average kinetic energy. Remember, kinetic energy is what? Energy of motion. So temperature is a measurement of the average kinetic energy of that item. So remember we've talked about the Kelvin scale, Kelvin degrees. So when we talk about Kelvin degrees, 0 degrees Kelvin, 0 degrees Celsius is 273 degrees Kelvin. The Kelvin scale was created by a guy who said, hey, wait a minute. Well, 0 is when, effectively when water freezes and becomes a solid. What happens when and again, they kind of knew that temperature was a measure of kinetic, the average kinetic energy at that point. So he says, wait a minute, at what temperature will everything stop moving? Because remember, all atoms, as they sit there, even in a solid, the atoms vibrate. And so temperature is still a measurement of that kinetic energy of vibration of those atoms, even in a solid. So if you got a, solid, I picked up a pen. That doesn't work when you're using a green screen. So when you have a solid, even though it's a solid, there's still atoms in there, and depending on the temperature, those atoms are still vibrating at a certain rate, depending on their temperature. The higher the temperature of this pen, the more those atoms inside that solid are vibrating with more energy. Because again, temperature is a measure of energy, of motion, kinetic energy, vibrational particles in a solid. So this guy, Kelvin, said, hey, listen, what happens when the molecules stop vibrating? That would be what we call absolute 0. So when molecules physically stop vibrating in a solid, they have no kinetic energy, so you would reach absolute zero. Now, here's the thing. Can we reach absolute zero? No, not really. We can't get all the energy out of a solid. We can get really close. We can't get it all out. Um, we don't have the capability of removing all the energy of the atoms of a solid as of yet. We can get pretty close. We can get within a degree or two, but we can't get it all out. So so it's basically 0 degrees Kelvin means all the energy is out. So remember, so that, kind of, let's go back to this. So it says, as temperature rises, individual molecules move faster. So in a solid, they would be vibrating faster. In a liquid, they'd be kind of expanding and, bumping into each other and moving around a little more. But in a gas, remember, all these atoms are free roaming around. So as temperature rises, the individual molecules move faster. As they move faster, remember, they're bing, 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 bing. It's a big pool table. They're all bouncing into each other. The faster moving molecules run into each other with more energy. So, when the linebacker weighs 100 pounds and runs into the running back, it just there's a small collision. When the linebacker weighs 200 pounds and runs into the running back, it's a bigger collision. When the linebacker is 240, like Luke Kuechly, and runs into the running back, it drives the running back backwards and into the ground. So, the larger, the more, the faster the molecule is, the more mass it has, the more energy it has when it runs into something. So just think of, the more energy something has, it's like it moves faster. So they transfer that energy with their collisions. Now, given, if this one's sitting still and this one moves into it, hits it, and this one moves off, and this one's still, so that's a 100% transfer. That rarely happens. Most of the time, these things are bing, and they just change directions. Bing. It looks like an old game of asteroids. Well, without things coming apart, because that would be a nuclear explosion. But anyway, so it looks like a bunch of billiard balls, and they don't all, the balls don't stop when they run into each other. They just change direction. But again, as they move, it's hard to, think of it, as you're moving them faster. But the higher the temperature, the faster these balls are moving. So this leads to collisions. Soon enough, molecules are pushed, and eventually, as you keep jacking up the temperature, these molecules are running into each other with enough energy. They push each other further apart. So in a cold gas, the molecules are all down here like this. And as you raise the temperature of the gas, the molecules are further apart as they're moving around. There's more space in between them. If they are further apart because of their energy, then the number of molecules in our box has to have more space around them. So again, if we imagine that box from the previous example, remember we said with the temperature the same and the pressure the same, we have this certain number of molecules. Well, if we raise the temperature, the number of molecules that are happily sitting in that box at a certain pressure goes down. So we raise the temperature and there's fewer molecules in our box because the pressure remained the same. When we're talking about the pressure of the molecules on the outside of the box, that's where we kind of run into this conundrum of wait a minute, what are we talking about? So when we raise the temperature, the molecules get further apart. So if there's molecules are further apart, so again, if you're thinking of something, it's, oh yeah, the width of the screen here. So how many molecules are going to fit in this space? Because again, we're talking air pressure. We're talking a vertical column of air going straight up and down. Well, if there's more space in between the molecules in there, there's going to be fewer molecules in that column. There'll be fewer molecules in our box, and our air pressure will be less because again, there's fewer molecules. The gravity has less to act on. Doesn't pull down as much stuff. Thereby, the air pressure goes down. Since the box is the same size, there'll have to be more space between the molecules, and then fewer molecules will fill in the box. Imagine a bowl of Rice Krispies. So, Rice Krispies are very small cereal pieces, right? So if you raise the temperature, so we have to expand the space between, the rice, the cereal things. So imagine a bowl filled to the same level with Fruit Loops. Fruit Loops are a much larger piece of cereal, aren't they? So if you think about the number of Rice Krispies versus the number of Fruit Loops, be far fewer Fruit Loops in that bowl than Rice Krispies. That's kind of what happens when you raise the temperature. Because of the space each atom needs, there's going to be fewer atoms in your bowl. Since our faster molecules need more space, there will be fewer of them in our box. Fewer molecules means less mass. Less mass means less weight. Lower weight is perceived as lower air pressure. So the higher the temperature of a mass of air, the lower the air pressure will be, because there's more molecules, there's more space between the molecules. Okay? So this is the end of our lesson again for the second day here. So again, kind of a short lesson. Gonna run through it again. So different ways air pressure can change. One, you put water vapor into it. Water vapor is a lighter and smaller, lighter molecule. So and again, going back to Avogadro, who says for any given space, you can only have so many molecules in it. And if we put a lighter weight molecule into it versus, that kicks out a heavyweight molecule, the stuff that's in there has less mass, less weight, less air pressure. So the amount of water vapor in the air can change the air pressure. And then down here, the temperature can change the air pressure. The higher the temperature, the more space between the molecules. The more space between the molecules, there's physically fewer in the area that we're measuring, and fewer means lower weight. Lower weight means lower air pressure. Any of you guys have any questions over this, please remember, give me a call, 704-363-9034, or text me. Remember to like this video. Remember to check in and say, hey, I was here for the attendance in the video comment section. Please subscribe to the channel. Make sure when when the next video drops for the next day. And we'll catch up with you guys at a later point. I hope everybody's out there still remaining safe. They've put a cap, they say we're going to get out of quarantine on the 8th of May. But they don't, I don't think they're talking about, haven't really said whether we're going back to school or not yet. But we will get out of quarantine right now on the 8th of May. I will say, with some of the other states kind of opening up, Georgia kind of wants to do it, and I think South Carolina's trying to do it. If their results between now and that date are good, yeah, they'll probably stick to the 8th. If suddenly you see a spike in cases in South Carolina and Georgia where they've tried to open up earlier than everybody else, they may change that. So if you're paying attention to the news at all, pay attention to the number of cases in South Carolina and Georgia where they're trying to open up, and that may give you an indication of what's going to happen on the 8th here. So we got about 2 weeks left in quarantine at this point. Yeah, about 2 weeks in a day or two. We're going to keep doing this until they let us back. So I hope you guys are at least paying attention to these videos. I really, is this the way I imagine things going? No, not really. I hope you guys are at least getting something out of this. And as we get into a little bit further into this, after this, we're going to talk about wind, and then talk about clouds and cloud formation and cloud types, and then get into weather. And so once we get into weather, we'll start, seeing some more things. I'll take us outside and look at some things like that. So especially with clouds, clouds will go out, and with wind, and show you some things outside. And I'll ask you guys to do some things outside with, with the clouds that you can see from your backyards. So anyway, we'll catch you guys on Monday. Have a great weekend. This is the Friday edition of the ACE Academy 7th grade science from the Brenner Bunker in the quarantined Southeast U.S. Have a fantastic rest of your day.